Our project is The Effect of Mass on the Gravity of an Object in Water by Kirsten and Toxie Hall Givens IV. We asked ourselves the question, does an object's mass affect the amount of gravity acting upon it within water any differently than that of air?
Our question basically asks if the Earth's gravity acts different upon an object falling through air than that same object falling through water, and if that difference is the same across all masses. In the simplest terms, does a light object fall as fast in water than it does in air? And do light and heavy objects differ between the two substances in the same way?
Humans only recently discovered gravity in the last 300 years or so. In the beginning of the 1500s, astronomers like Galileo and Brahe discovered that the Earth and other planets revolved around the Sun. Kepler showed that they moved in an elliptical orbit, not a circle. This is when gravity was discovered by a man named Sir Isaac Newton. He was a mathematician and a physician who lived from the time 1642 and 1727. The legend is that Newton discovered gravity when he saw a falling apple while thinking about the forces of nature. Whatever happened that day, Newton realized that some force must be acting on falling objects like apples because otherwise they would not start moving from the rest. Newton also realized that the moon would fly off away from the Earth in a straight line tangent to its orbit if some force was not causing it to fall toward the Earth. The moon is only a projectile circling around the Earth under the attraction of gravity. Newton called this force gravity and determined that gravitational forces existed between all objects. Then Albert Einstein stepped in. He described gravity as not a force but as a consequence of the curvature of space-time caused by the uneven distribution of mass. According to Einstein, gravity arises from the warping of space-time. Einstein's new theory of gravity explains a number of phenomena that would violate Newton's theory. For example, light bends when passing near massive objects like the sun, and a clock raised above the Earth speeds up relative to a clock on the surface. So the closer objects are to each other, the stronger the gravitational pull is. Earth's gravity comes from all its mass. All its mass makes a combined gravitational pull on all the mass in your body. That's what gives you weight. And that's what gives all objects weight. Drag is a force acting opposite to the relative motion of any object moving with respect to a surrounding fluid. Friction is a force that opposes the motion of objects. Friction can cause objects to slow down. Air resistance is a type of friction. Air resistance causes moving objects to slow down. In a similar manner, water exerts a net drag force on an object and tends to make the object move along with the average water flow, or stay put if the water isn't going anywhere. If an object with mass is dropped in water, the friction allows the object to pull on the water and the gravity pulls the object down to the surface. This is due to liquid molecules being not in a rigid state and sliding over one another. Our materials were as follows. The first material we used was an 11-inch tall container of water. The second material we used was a body of air. The third item we used was a ruler. The fourth item we used was 3 different weights, 100 grams, 50 grams, and 20 grams. Our fourth material was a stopwatch. Our fifth material was paper towels. Tad and I's proposed hypothesis is that the more mass an object has, the stronger the pull of gravity is. Therefore, the weight with the highest amount of mass will fall fastest, whether in water or in the air. In our experiment, we conducted 3 trials for water and 3 trials for air. We did these trials for each weight, where the masses are 100 grams, 50 grams, and 20 grams. Our results were as follows. In our water trial, the 20-gram weight dropped at 0.52 seconds in the first trial. The second trial came to 0.50 seconds, and the third trial, 0.53 seconds. With our 50-gram weight, the first trial proceeded to be 0.49 seconds. In our second trial, it was 0.47 seconds, and in our third trial, it was 0.50 seconds. In our 100 grams trial for water, trial 1 showed 0.42 seconds, trial 2, 0.44 seconds, and trial 3, 0.42 seconds. In our trials for air, the first weight of 20 grams during trial 1 dropped at 0.48 seconds, at trial 2, 0.50 seconds, and at trial 3, 0.52 seconds. Our 50-gram weight dropped trial 1, 0.48 seconds, trial 2, 0.43 seconds, and trial 3, 0.47 seconds. And finally, our 100 grams weight trial for air at trial 1 dropped 0.36 seconds, trial 2, 0.40 seconds, and trial 3, 0.35 seconds.
When we averaged the results found, we came out to having an average water trial of 20 grams being 0.51 seconds, average water trial of 50 grams being 0.48 seconds, average water trial of 100 grams being 0.42 seconds, average air trial of 20 grams being 0.50 seconds, average air trial of 50 grams being 0.46 seconds, and the average air trial of 100 grams being 0.37 seconds. From these results, we can conclude that the water resistance is much stronger than that of normal air resistance and drag. We can also conclude that when an object has a heavier mass, it both falls faster and is affected the most by water resistance. The 20-gram weight had a difference of only 0.01 seconds when comparing the water time to air time. The 50-gram weight had a difference of 0.02 seconds, and the 100-gram weight had a difference of 0.05 seconds. We can come to the conclusion that our hypothesis was correct. However, there is potential human error within our apparatus. The experiment was performed by hand, dropping each weight from a measured 11 inches while hand timing the fall with a stopwatch. This leaves 3 potential errors. The first being that we could have dropped the weights differently each time at a different angle. The second being that we may have been above or below the measured 11 inches. The third being that we could have been delayed or prematurely stopped the stopwatch. Despite these errors within the apparatus, we believe that they do not hold much significance due to how the data collected resulted. This experiment has direct ties to multiple concepts within physics. Gravity and resistance, being water or air, are the 2 major focuses within the study. As stated earlier, gravity plays a significant part in holding up the ideas of relativity and space-time. While we only focused on a smaller Earth portion of gravity rather than how the gravity of 2 different objects interact with each other, the underlying principles remain the same. We also dived into the minute and subtle differences involving acceleration and resistance, how a liquid, like water, can make small changes to an object's acceleration, such as 0.01 seconds, compared to an object's acceleration in air. While the intricate depth isn't fully tackled with this experiment, it serves as a way to grasp the impact that these physics concepts may have on everyday life.